Good morning, or good afternoon, or good evening, wherever you may be. I am Charles McGee, Chief Scientist of the Material Sciences Division of EAG Laboratories, and today, using secondary ion mass spectrometry, I'm going to try to tell you everything you ever wanted to know about analyzing vertical cavity surface-emitting lasers, but were too afraid to ask. That last bit being taken from a 1972 Woody Allen movie. So, let me tell you a little about myself. I received my BS in chemistry and my PhD in analytical chemistry from the University of Virginia, where my thesis topic involved elemental mass spectrometry of solid materials, which is essentially what I still do. Immediately upon graduation in 1973, I took a position as member of the technical staff in the Materials Characterization Research Group at the David Sarnoff Research Center, the Central Research Division of RCA Corporation here in Princeton, New Jersey. My direct supervisor there was Richard Honig, the author in 1958 of the first published paper on secondary ion mass spectrometry. He guided me and gave me encouragement as I designed and built my very own SIMS instrument from scratch. With the purchase of RCA by General Electric in 1987, I decided to leave and co-found Evans East, an East Coast laboratory associated with Charles Evans and Associates. The two entities were merged in 2005, and the Evans Analytical Group was born. As the slide shows, I have more than 45 years of experience in performing SIMS analyses. EAG is the global leader in advanced surface analysis and materials characterization. We have over a 30-year history. We have over 7,000 active customers. Our employees number over 1,200, many with advanced degrees. We have 21 locations worldwide, 13 labs in the U.S., and we have the largest equipment set of any commercial lab network. The Material Sciences Division of EAG has 23 locations of labs and sales offices in 10 countries and 4 continents, covering all of the major areas where semiconductor R&D and manufacturing are located. The Materials Sciences Division has over 300 staff, with over 100 of those holding advanced degrees. We have more than 40 analytical techniques and over 180 test methods that we can bring to bear on any given problem. And we do that with a $150 million installed equipment base. And we are a trusted partner in supporting R&D efforts to accelerate time to market with surface, bulk, organic, semiconductor, and metallurgical analyses. Now, EAG's approach to analysis is to work with clients at the beginning stages of an investigation to help define the problem and goals, and to determine the best approach and helping to design the experiment whenever possible. When we perform the agreed upon analysis, but we always keep a lookout for unforeseen things in the data that may be of significance, and that is where our analysts' years of experience really comes into play. We then help you to understand the data with a detailed report when necessary. And in the end, we have to ask if the goals have been met and if further analyses will be required. And as shown in red, if you put more time and effort into the planning stages, then we will have to spend less time and less of your money in the actual analysis stage. So why use SIMS? As you will see, SIMS has lots of pitfalls and difficulties. So why do we keep using it? The answer is sensitivity. The sensitivity advantage of SIMS is shown dramatically in this slide. It is the EAG bubble chart. It shows where many techniques fit into the analysis space of analytical spot size at the bottom of the chart, and detection limit shown in atoms per cubic centimeter on the left and in atom fraction on the right. There are many techniques that have much smaller analysis areas than SIMS, but these only have detection sensitivities of between 1% and 0.1% atomic. Only dynamic SIMS shown in the blue bubble reaching all the way to the bottom of the graph. Only dynamic SIMS has detection limits below 10 parts per billion with analysis areas of less than 10 micrometers. And these detection limits can be obtained with high depth resolution. There are some techniques that also have good sensitivity, but these are bulk analysis techniques, and these are shown outside the graph on the right. There are also techniques with much smaller analysis areas than SIMS, but these are imaging techniques only, and they are shown above the graph. This presentation is going to show characterization of VCSELs by SIMS, but we're also going to show at the end some examples by transmission electron microscopy. So I should go over the capabilities that the EAG has in both of these characteristic areas. In SIMS, we have 50 SIMS instruments, and that allows us to optimize each instrument for specific applications and materials. That way we get much better detection limits than labs that only have 1 or 2 instruments. We have magnetic sector-based tools, we have quadrupole-based tools, and we have time-of-flight-based tools. In transmission electron microscopy, we have 8 TEM and STEM instruments. STEM is scanning transmission electron microscope. We have an FEI ORISIS with new levels of EDS detection sensitivity, and EDS is X-ray dispersive X-ray spectrometry. And we have an Hitachi HD 2700. It's an aberration corrected STEM. And we have 10 dual beam focused ion beam tools for sample preparation. This slide shows in block form what makes up a secondary ion mass spectrometer. We have an ion source shown on the left, and in that source we produce ions of either oxygen or cesium, and these ions impact the sample and sputter the sample. The material sputtered from the sample is mainly neutral, uncharged, and we cannot use that material. We can only use the material that is sputtered from the sample as positive or negative ions, and probably 99.99% of the material sputtered is neutral and unusable. So the positive or negative ions are extracted and focused into the mass spectrometer. And then the selected mass is impinged on the detector, and we can display the data in a number of ways. We can simply take a mass spectra to determine what is present. We can obtain an XY ion image, a spatially resolved image of the location of the element of interest. But most often we do a depth profile, and that is done by monitoring the masses of interest as the sputtering continues. And as you sputter, the surface recedes into the bulk. So if you monitor species with respect to sputtering time, it naturally generates a depth profile, which is the distribution of the elements of interest with respect to depth. This slide illustrates the principles by which EAG's 3 types of SIMS instruments mass resolve secondary ions. On the right is the traditional method of mass analysis where ions are separated according to their mass-to-charge ratio in a magnetic field. Ions of the desired mass pass through a slit at the exit of the magnet, while ions of lower or higher mass are not passed. In the center is shown how a quadrupole mass filter separates ions with respect to their mass-to-charge ratio. Radio frequency AC waveforms are connected to opposing pairs of rods, which also have positive or negative DC voltages applied to them. Ions of a certain mass will only traverse the length of the rods for a specific amplitude of imposed RF and DC voltages. On the right is how a time-of-flight mass spectrometer works. Secondary ions are formed in a short pulse by a pulsed primary ion beam. Once generated in a strong accelerating electric field above the sample surface, the light ions will have a higher velocity than heavier ions and will arrive at the detector before the heavier ones. Thus, the secondary ions are separated in mass-to-charge ratio by measuring their arrival times at the detector. We use all three types of SIMS instruments at EAG. Each has its strengths as well as its weaknesses. Traditionally, SIMS has been used for dopant and impurity concentrations. However, compound semiconductor development has desired more information: improved dopant gradient and abruptness accuracy, precise location of dopant and impurity elements, group 3 and group 5 composition in very thin layers, for instance an etch stop, group 3 and group 5 composition gradient analysis, and accurate layer thicknesses. However, most SIMS analyses are carried out in a matrix of fixed composition, i.e. silicon or gallium arsenide. 3,5 materials present unique difficulties because the matrix often changes with depth. This change in matrix composition changes elemental sensitivities, changing sputter rates. It changes everything. This is certainly the case when analyzing VCSELs by SIMS. And for that, we invented P-core SIMS, shown in red at the bottom of the slide. One of the biggest challenges associated with the application of SIMS to the analysis of AlGas pixels is the variations in aluminum content, which impacts sensitivity of aluminum, the SIMS matrix effect. This means that quantification of aluminum content is not straightforward. Complicating matters further, changes in alloy composition also affect the sensitivities of the dopants and impurities measured in the depth profile, the infamous SIMS matrix effect. P-core SIMS, that is point-by-point corrected SIMS, addresses these problems by employing empirically derived analytical functions to correct for the SIMS matrix effects as they come into play when one deals with materials that are dissimilar in nature. These corrections can be made for group 3 elements, dopants, and impurities alike. And the changes with respect to composition occur on a point-by-point basis. That is, for every impurity or dopant data point, the matrix composition is determined and the corrections are made according to the measured composition at that data point. We devised P-core SIMS analytical functions by analyzing known amounts of dopants and impurities in a series of aluminum gallium arsenide materials ranging from gallium arsenide to aluminum arsenide. This shows how the sensitivities for carbon and silicon, the most often used P and N-type dopants in VCSELs, vary with aluminum composition. The difference in sensitivity can be as much as a factor of 3. Now I should note on the slide that the vertical axis is relative sensitivity factor. And this is a term that is needed in the quantification, but you should realize that there's an inverse relationship between relative sensitivity factor and sensitivity. So as the aluminum composition goes up, going from left to right on the graph, the sensitivity of carbon and silicon actually go down. And as we shall show, VCSELs have aluminum content varying from 10% to 99% group 3 atom fraction. So these differences in sensitivity need to be accounted for. If not, seriously inaccurate doping concentrations will be reported. We verified the accuracy of our P-core SIMS corrections by measuring ion implants of carbon and silicon across the interface of an aluminum 0.8 gallium 0.2 gallium arsenide structure. Plotted using the solid lines are the carbon and silicon implant profiles using only gallium arsenide sensitivities. There's a large discontinuity at the AlGas gas interface, which is an artifact due to the change in sensitivities between the two layers. However, after applying the P-core SIMS corrections at each data point in the dashed curves, the anticipated implant profiles are obtained with no discontinuities at the interface. As noted on the slide, without P-core SIMS corrections in the AlGas, the concentrations of carbon and silicon would be too low by a factor of 2. The next slide shows the ramifications of the effect of the P-core SIMS corrections on an NdBr. This slide shows the silicon doping profile in an N-type DBR using only gallium arsenide sensitivity for silicon, that's the red curve, and with the P-core SIMS corrections applied, that's the green curve. As expected, where the aluminum content is low, the two curves are close together, and that's showing that there's not really much error in using only the gallium arsenide sensitivity factor. However, in the DBR layers with very high aluminum content, the difference between the two curves is very significant indeed. In fact, without the P-core SIMS correction, the silicon profile would lead one to believe that there is actually more silicon in the low aluminum layers than in the high aluminum layers, which is actually the opposite of what is actually occurring. You can see how important the P-core SIMS correction really is. But not only must we get the elemental concentrations correct, but we also must get the layer thicknesses correct. There is a large change in composition between layers, and this complicates matters. As shown in this slide, we normally determine the depth of each data point by multiplying the sputter time of each data point by the sputtering rate. One normally determines the sputtering rate by measuring the depth of the sputtered crater and dividing by the total sputtering time. However, the sputtering rate varies in 3-5 materials with composition, so one needs a correction scheme to get the layer thicknesses correct. And the next slide just shows just how significant this sputter rate change is. The change in sputter rate between high and low refractive index layers in the DBR can be as much as 25%. P-core SIMS uses this empirical relationship between sputter rate and aluminum content to correct the sputtering rate for each data point depending on the aluminum content measured at each data point. Composition quantification, and in fact all quantification, is dependent on having accurate reference materials. The reference materials we use for determining the aluminum composition in VCSEL layers are all cross-referenced back to two standard reference materials, that's SRMs, issued by the National Institute for Standards and Technology. Note the low level of error in the NIST certified aluminum mole fraction, that's 0.7% relative. We consider these two SRMs as being crucial to our ability to have confidence in our reported AlGas compositions. Using these SRMs, we have shown the ability to determine aluminum gallium group 3 atom fractions over a wide range of aluminum compositions, as shown in the next slide. This shows the aluminum and gallium profiles in a stair-step sample with multiple layers of aluminum and gallium arsenide layers, with aluminum group 3 fractions ranging from 0.07 to 0.79. And note that all of the SIMS determined compositions are within 5 relative % of the values determined by Rutherford backscattering spectrometry, which is quantitative from first principles. So now, on to vertical cavity surface emitting lasers. The VCSEL was first commercialized in 1996. Its main applications for the last 20 years have been high-speed data communications, especially with optical fibers, computer mice, laser printers, and some recent applications are light imaging detection and ranging, and 3D sensing and facial recognition. There's a VCSEL pointing at your face in virtually every modern cell phone. The VCSEL has the advantage of low-cost manufacturing, on-wafer tests, good reliability, high optical efficiency, and large 2D arrays can be fabricated for increased power. EAG has performed SIMS analyses on VCSELs for almost 20 years. SIMS results have been used for reactor ramp-up, product monitoring, process improvement, and failure analysis. Now, the advantages that the VCSEL has over its edge-emitting cousin come at an expense of a more complex device architecture. With a VCSEL, resonator mirrors have to fulfill two roles. Like an edge emitter, they have to control the extent of optical feedback and light output. But in addition, they also have to be electrically conducting so they can aid in the injection of carriers from the contacts into the active region. This set of requirements is met by forming a stack of semiconductor layers which have thicknesses that are carefully chosen to create distributed Bragg reflectors. To produce high-performance VCSELs, the DBR is formed from alternating layers with sufficiently high refractive index contrast to realize high levels of reflection. Engineers must also ensure that the conductivity of the mirrors is sufficiently high to prevent excess ohmic heating when injecting current into the active region. High-efficiency VCSELs are possible when these mirrors form a part of a structure with a high degree of optical and electrical confinement. Such a device may be built from more than 200 layers, some of which contain grading of both the dopant level and alloy composition. Growth of such a structure is very challenging, so process engineers support their efforts by using a variety of characterization techniques to uncover details associated with the epilayers, such as their thicknesses, doping, and composition. While some approaches offer insights into a few of these characteristics, one is capable of delivering a great deal of detail about these structures, and that is P-core SIMS. Producing high-performance VCSEL requires optimization of various aspects of the device, including the aluminum composition and gradient between high and low refractive index mirror layers, the dopant profile between the mirror layers, the composition of the aperture layer, assuming it's an oxide-confined VCSEL, the active layer impurity content, the aluminum grading on either side of the active layer, and of course the thickness of all the layers within the structure. An example of a P-core SIMS depth profile of a complete VCSEL is shown in the next slide. This particular wafer uses a carbon-doped P-type AlGas DBR, a silicon-doped N-type AlGas DBR, and an undoped low aluminum AlGas active layer with a multi-quantum well. And this particular sample is one that we designed ourselves and had one of our customers fabricate for us because we could not use an example of a real customer sample that we use in our analytical service business. If the DBR is to provide good current injection, it must have low electrical resistance. Realizing this in a manner that produces good device is not trivial. Large energy band offsets between the high and low index semiconductor layers of the DBR can inhibit current flow, particularly for the P-type DBRs. And the obvious solution of increasing the dopant to term resistance is not an option because this increases optical absorption. A far better approach is to grade the AlGas composition at the interfaces while varying the doping profiles at these points. And in due course, we'll show how a P-core SIMS is uniquely capable of measuring the subtle alloy grading and interface doping profiles. You can see in this slide that plotted to the left axis are the carbon, boron, and silicon concentrations. You can see the carbon in the top P-type DBR and the silicon in the bottom N-type DBR along with oxygen impurities. And the boron is simply to mark the substrate interface. To provide current and optical confinement, producers of VCSELs tend to introduce a high aluminum content aperture, which we can see in this slide here. And the aperture is oxidized from the outside inward. Halting the process at an appropriate point leaves an unoxidized aperture through which the current and light can pass. Obviously, to have a repeatable oxidation process, the rate of oxidation must not vary. This implies that there must be stringent composition control and uniformity of the aluminum gallium arsenide layer because the oxidation rates vary by more than 2 orders of magnitude when the aluminum content is increased from aluminum 0.82 to aluminum 1.0. With P-core SIMS, the aluminum composition of high aluminum content AlGas layers, such as those used in forming aperture layers, can be determined with a high level of precision as shown in this figure. In these examples, the difference in aluminum content between these two samples is only 1.8% of the group 3 composition, or 0.9% of the total atoms, but the spread in measurement values of either film is much less than this. This degree of precision is crucial in perfecting these aperture layers. And we have used our novel P-core SIMS technique to analyze the VCSEL structure with a carbon-doped P-type gallium arsenide DBR, a silicon-doped N-type gallium arsenide DBR, and an undoped low aluminum AlGas active layer containing a multi-quantum well. The remainder of this presentation will show how our technique can offer insights into alloy composition profiles, the DBR dopant profiles, and various details of the active region. So let's look at the carbon in a P-type DBR. This slide shows how carbon is present in large spikes at the interfaces between the high and low refractive index layers and in smaller spikes within each layer. The larger spikes are intentionally added doping spikes. The smaller spikes will be discussed in the next slide. But before we go on, this slide points to the importance of using our P-core SIMS corrections to carbon sensitivity. You can see how using only gallium arsenide sensitivities, that's the red curve, the carbon doping spikes at the interfaces would be underreported by a factor of 2 compared to the P-core SIMS profiles, that's in the black curve. The slide also demonstrates the ability to resolve these spikes even though they are only 2 nanometers thick. But for a more detailed look at the PDBR region, let's look at a higher depth resolution analysis of the top of that DBR. As previously mentioned, grading the alloy composition between the low and high index layers can trim the resistance of the DBR. With our P-core SIMS technique, it is possible to hone in on this part of the structure with a higher depth resolution profile of the top 200 nanometers of the sample and reveal the composition grading. This occurs because the aluminum gallium are not simply switched on and off, but varied in a precisely controlled manner to optimize the optical and electrical properties of the interfaces. You can see how the sloping blue line of the aluminum is not straight. It's actually formed in 2 discrete steps going up and 2 discrete steps going down. Measurements with P-core SIMS have determined the aluminum content correctly over the entire range of composition from 8% to 83% aluminum. The accuracy of these measurements has been verified using the standard reference material 2841, which I showed earlier. Further reductions in resistance of the P-type DBR are possible by doping the mirrors with carbon, which has a sensitivity that is significantly affected by alloy composition. However, with P-core SIMS, we can correct for these effects at every data point. That's very important, at every data point, because the aluminum composition is measured for every carbon data point. Such an approach uncovers a high concentration carbon doping spike in some structures, which is near but not exactly at the interface. And you can see that here in this slide. We are confident that the placement of the carbon doping spike is correct because all of the profiles were acquired in the same analysis. And note how the low-level carbon doping spikes may originate from a non-uniformity in doping while the wafer was rotated during growth. But P-core SIMS can also provide insights into the structure of the active region, which is circled here in red. P-core SIMS can reveal the aluminum profile, which varies on both sides of the active layer. There is a grading from the P-type aperture layer and also from the N-type DBR to the cladding layers, where it is followed by a steep drop in aluminum content, which is lower in the barrier layers immediately surrounding the aluminum gallium arsenide active layer. The detailed picture of the active region is also helpful in assessing whether the lasing mode in the optical cavity is in the optimal position. The profile of the active region in this slide also details the carbon doping for the active region and the mirror pairs nearby. By measuring the carbon and silicon concentrations accurately in the N-type DBR with P-core SIMS, it is possible to determine the amount of P-type counter-doping that the inadvertent carbon contamination causes in the N-type layers. And if you will notice, this profile starts at a depth of less than 100 nanometers. And that means that we have etched off almost the entire PDBR layer before starting this analysis, and we've developed very sophisticated etching techniques where we can stop the etch at any layer in the DBR that we choose. And this allows us to analyze the active region under higher depth resolution conditions than we could use if we had to analyze the entire structure. Another strength of PCOR SIMS is its ability to profile unwanted contamination species. The most ubiquitous of these is oxygen, which can produce contamination spikes at the growth transition between the high and low index layers of the PDBR. Knowing the exact location of the oxygen spike in the growth sequence is often helpful in trying to isolate and eliminate the source of contamination. Occasionally, VCSELs contain sulfur impurities, which are believed to affect performance. The level of sulfur is typically higher in the PDBRs than in the NDBRs. The peak in the upper graded AlGas cladding layer is easier to spot in the higher resolution analysis of the active layer in the next slide. This slide shows how the sulfur contamination peak is actually located in the middle of the grade of the aluminum in the P-type cladding layer. Obviously, another prerequisite for the successful growth of a VCSEL is to accurately control the thickness of the many layers that make up a working device. Nowhere is this more important than in the DBR, where the thicknesses must be correct to tailor the optical properties of the mirrors. Determining the correct layer thickness with conventional SIMS is not easy because changes in alloy composition alter the sputtering rate. If no corrections are made, that's the red curve, the plotted layer thicknesses can be in error by approximately 20% with respect to the PCOR corrected profiles, which are in blue. With PCOR SIMS, this weakness is addressed by the empirically derived sputtering rate function that I showed earlier. This determines the instantaneous sputtering rate for each data point based on the measured aluminum content or indium content for InGas active layers. Armed with this approach, compensation corrections are made for variations in sputtering rate throughout the VCSEL. The accuracy of the PCOR SIMS protocol in determining layer thicknesses can be seen in this slide, which is an overlay of a PCOR SIMS analysis of the active layer of a VCSEL with the cross-section TEM micrograph of the same region. The agreement in layer thicknesses between the PCOR SIMS and the TEM is quite good. However, the SIMS profile for aluminum does not resolve the MQW region as well as the TEM appears to. Fortunately, we have many techniques to bring to bear on a problem, so we can use TEM to better resolve the true aluminum content in these thin multi-quantum well laser areas. This slide shows a scanning transmission electron microscope image across the bottom of a multi-quantum well region, along with an energy dispersive X-ray spectrometry line scan across that same area. Here, the aluminum levels are fully resolved in the EDS line scan into layers of discrete composition, which is not possible with SIMS due to the energetic ion bombardment needed to generate secondary ions. STEM EDS line scans can also be used to evaluate the thickness uniformity in the multi-quantum well layer across the device. The image at the top shows two regions from which higher resolution images below were taken. The layer thicknesses and error bars are shown in green, and I'm sorry if they're hard to read. The error of 0.2 nanometers suggests that there are no thicknesses difference in the high Z, those are the lighter layers, but there is in the low Z or darker layers. However, we can do analyses not only on epi wafers, but we can do analyses on actual finished, fully processed devices. This is an example of doing a SIMS analysis on a finished VCSEL. The images to the left show the original sample, that's the top. However, there's metallization on this, and we have to remove the metallization before we do the analysis. And this requires great care in mounting the sample and polishing off the metal so the analysis can be made. The bottom two images on the left show where SIMS craters have been put into the device, and they're to two different depths. That's why they look different. The data in the right panel show aluminum plotted in counts per second with respect to the right axis, and profiles for carbon, silicon, oxygen, nitrogen, fluorine, and chlorine plotted in atoms per cubic centimeter with respect to the left y-axis. And you can see how even in these small analytical areas of some 10 or 15 micrometers, we can get very good detection limits indeed. But as I indicated in the very beginning of the presentation, we have many tools to bring to bear on a problem, not just SIMS. In this example, we will be showing scanning transmission electron microscopy, STEM, analyses for failure of a VCSEL. This is a unique case where EAG worked with a team of CERN scientists to capture the initial creation of dark line defects, that's DLD, networks through very sensitive reliability testing at elevated temperature and humidity. In this case, we were able to stop the test at the very first signs of degradation, and this is what we found. We performed plan view and subsequent cross-section measurements of the plan view sample. They clearly showed the very beginnings of a DLD network that starts at the aperture edge. Now, these VCSELs were installed in the ATLAS detector at the CERN Large Hadron Collider. They have 6,000 optical data channels in this detector, and they were having premature data link failures. That's 600 failures in 2 years. And this is a problem because the detector is located in an unusual place, in an underground cave that's kept at 24 degrees C and 40% relative humidity. This slide shows a cross-section of a focused ion beam cut into a failed VCSEL from the ATLAS detector. The aperture is noted in the center of the image, just above the multi-quantum well active region. The PDBR and the NDBR are also shown. The portion of the device shown in the yellow box will be shown in greater detail once this portion of the sample has been lifted out of the VCSEL. The image on the right side of this slide shows two VCSELs. One of those two, the one on the left, is as received, and the one on the right has been cut by a focused ion beam to lift out a thin section of the sample for STEM imaging. The imaging on the right side of the slide shows a plan view of the oxidized AlGas aperture in which you can start to see a large DLD network. That's the light, fractal light pattern that is formed, resulting in device failure. Looking more closely at this region from the left side of the plan view image in the previous slide, the upper center image, the red box, shows a small section of the DLD network. That portion of the sample was then cut out with a focused ion beam and imaged in cross-section, shown across the bottom of the slide. The edge of the aperture is at the extreme right of the image. The DLD network can be seen in the red box above it. It can be traced to the corresponding features in the cross-section image below it. This reveals that the DLD network is mainly in the MQW region, but can also be seen to have propagated into the NDBR below the active region, displaying an out-of-plane dislocation behavior. This slide shows the actual effects of the defects that have on light emission of a VCSEL. The image on the left is of the optical emission of the device that it is just starting to fail. You can see the dark area pointed toward the left edge of the image. This is the same area. When this same area is STEM imaged in plan view, you can just start to see the defect network forming at the aperture edge. The defects are seen more clearly in the higher magnification image below it. So from the conditions used from the acceleration age test, the CERN scientists have concluded that it is very important to keep moisture out of these devices. So in conclusion, EAG's development of an advanced form of SIMS has opened up new capabilities for VCSEL analysis so that EAG can now measure group 3 atom fraction, including aluminum gallium arsenide composition and aperture layers, measure dopant and impurity concentrations, taking into account the changes in sensitivity due to group 3 composition, obtain correct layer thicknesses for different compositions, including graded changes in composition, all while maintaining nanometer depth resolution. And just so you don't forget about SIMS when working with VCSELs, the American Express company is currently running TV ads that say, "Don't do business without it," referring to the American Express card. You might wonder where this phrase comes from. For some of you old enough to be watching TV in the 70s, you might remember the American Express guy. He was played by Carl Malden, who played a detective on his TV series. And he was used by American Express in over 100 TV commercials. And his classic catchphrase when talking about the American Express card was, "Don't leave home without it." And this was the graphic that was associated with Carl Malden in those days. The American Express card, don't leave home without it. But when analyzing VCSELs, you should always remember the SIMS card. Don't leave home without it.